Welcome to another video in the graph series. Today we will be looking at the same question that we looked in the last video, but today we will be doing BFS, which is breadth first search, and we will be doing it on the adjacency matrix itself. So let's look at the question for a quick revision. So this is the graph examples that are given to us. Before we move ahead, I would just like to take a moment to remind you to be consistent and make sure you do not miss any videos in the graph series. So make sure you subscribe, hit the notification bell icon. You will also stay motivated, and you have no idea how much your support will mean to me. There's so much of free content available on the channel. There's HLD, LLD, DSA, Advanced C++, tutorials, mock interviews, and so much more. So if you think I deserve your support, please subscribe, hit the notification bell icon. And there's obviously a bunch of stuff that I cannot do on YouTube, like mock interviews, live interactive classes. So we have educourses.com, we have live courses, self-paced courses with live doubt solving support, which both of them we have mock interviews, and we have a lot planned in LLD, HLD, Advanced C++, DSA, and so much more. You have no idea. So if you want me to be part of your further learning journey process, please check it out. The link is in the description. And now let's continue. And we have to see if there is a path from source to destination. So there are n vertices. So here n is 3 and here n is 6, and we are given the edges. So we have to form the graph. So we will be using adjacency matrix to form the graph. And here we are given one source and destination. Here we were given 0 and 2, and we have to see if there is a path or not. So we will be applying BFS today. I have made graphs corresponding to both the examples that are given to us, and I have also made the adjacency matrices. I hope you have completely understood adjacency matrices by now, but if not, let's quickly look at them again. So here you can see that 0 is connected to 1 and 2, right? 1 and 2 like this. So that is why in the row 0, 1 and 2 is true and the 0th one is false. Similarly, if you see for any vertex, like for example here 5, 5 is connected to 3 and 4. So in the row for 5, only 3 and 4 is true and rest all of them are false, right? So for every node you can see what all are true. Those are the connected, those are the nodes with which we have a direct edge. Like for example here 2 has a direct edge only with 0. So here 2 has a direct edge only with 0, rest everything is false. So I hope you have completely understood adjacency matrices by now. Now we are going to see how BFS is going to work, which is breadth first search. In BFS, what do we need? We need first in, first out, and that is why, yes, which data structure are we going to use? Queues. Very good. Now, other than that, because we are dealing with graphs, we need another thing. What is that? Visited array. Yes, very good for thinking about it, for those who thought about it. So here, what will be the size of our visited array? It is going to be the number of nodes or number of vertices. Here we have 3 nodes, so I have made array of length 3, 0, 1, 2, and initially I am marking all of them as not visited. So we are going to start visiting the nodes from which node? It is given that 0 is our source node. So we are going to start from 0. I am going to push it to the queue and I am going to mark it as visited. So I am marking it as true. Okay, so this is visited. Now what do we do in BFS? In BFS, we push all of its neighbors into the queue. So who are the neighbors of 0? We are going to look at this row and see that, oh, 1 and 2, both of them are neighbors. So we are going to push both of them to the queue. And when we push them to the queue, at that time itself, we will mark them as true. Note that we should mark them as true when we are pushing to the queue itself, so that we don't end up pushing the same thing to the queue again and again, right? Like you should be able to think about it, that why are we not putting it true when we are popping it out? Why only when we are pushing it into the queue? And if you have any doubt, to the dry run, do when you are popping out, if I mark true at that time, what would have happened? Okay, so these details, it is very important for you to think about them. So now that I am done with all the neighbors of 0, I'm done with all the neighbors of 0, what am I going to do? I'm going to pop it out because I'm done with 0, right? Now because I'm dealing with queue, I am going to deal with the first or the topmost element or the first element that I had pushed, basically the first node that I had pushed. What will that be? It will be 1, correct? Now I will see the neighbors of 1. Who are the neighbors of 1? The neighbors of 1 are 0 and 2. But if I look at the visited array, both of them are visited. So am I going to push anything to the queue? No. See, this is where it comes into picture. If I had not marked them visited already, then, I would have gotten 2 as false. That would have been wrong. So I should mark the nodes as visited as I am pushing to them to the queue. So now I see that all the neighbors of 1 are visited, so I am not going to visit them again. I am done with it, so I am going to pop it. Then I come across 2 and I see, oh, this is the destination that I wanted. I am done with it, I found it, and I am going to return true. Let's try run for the second example as well. So again over here, we are taking a queue and we are taking a visited array. What will be the size of the visited array over here? It will be 6 because there are 6 vertices, right? So I am making 6 vertices over here, 0, 1, 2, 3, 4, 5. And initially, I'm going to mark all of them as what? I'm going to mark them as false because we have not visited any of them. Again, we are going to start from our source node, which is 0. So we're going to start from our source node. We are going to put it to the queue. So if I put it from here, I put it to the queue and I have marked it as true. Now, who are the neighbors of 0? The neighbors of 0 are 1 and 2. So we are marking both of them as true, as visited, and I am putting them to the queue, right? 0, 1, 2. Because I am done with all the neighbors of 0, I am done with 0 completely. So now what I am going to do? I am going to pop it out. I am done with 0. So now what was the first node that I had pushed? That was 1. I will consider the neighbors of 1. Now all the neighbors of 1, which are 0 and 2, are again visited. So do I need to push anything to the queue? No, I am done with it. So now I am ready to pop out 1. Then I am going to come to 2 and I am going to see who are the neighbors of 2. It was just 0 and 0 is already visited. So am I going to do anything? No, I am not going to do anything. I am going to pop it. Now the thing is that the queue is empty. So this means that we did not find our answer and we are going to return false. So our destination that is given in the question is basically 5. At any point, I did not find 5 in the queue. That means it is not reachable from 0, and that makes sense. If there was, say, a connection like this, then from 1 I would have pushed 3, and then from 3 I would have pushed 5, right? Because I am going level wise. I am going like this, like this, like this, like this. I am going level wise. But because I never reached 5, that means there was no path over there. So once the queue is empty, that means there is no path reachable to that node. So that means the answer over here is going to be false. Now let's try to convert this into code. I'll be first writing the code in C++. For Java people, you can go to this time and you can see the Java code. So here we are given the edges and we are given n. So first thing we have to do is form the adjacency matrix. Again, what will be the size of the adjacency matrix? It will be n by n, right? So I am making a vector of vector, and because it is not weighted graph, so I can just take Boolean itself. So I am going to call it graph itself. You can call it anything. You can call it adjacency matrix, and it is going to be n by n vector of bool. And I am initializing the entire thing by false. So initially nothing is connected to each other. Then I am going to go through the edges one by one and I am going to mark them true, right? So I go through all the edges one by one. So how do I go through edges? For every edge in this edges. So now in every edge there are 2 things. So right, so this is one edge. So we had done this in the last video as well. So there is one u, which is edge of 0. And then there is v, which is edge of 1, correct? And what do I need to connect? It is bidirectional graph, so I need to connect it both the ways. So how am I going to do that? Graph of uv, I am going to mark it as true, and similarly graph of vu, I am going to mark it as true, correct? Because it is bidirectional, please take care that you do not miss this step, and you do not need u and v. You could have just written edge of 0, edge of 1, but this is just to make things clearer. Okay, now we are done with forming our graph. Now we are going to start with a BFS. For BFS, we need 2 things, right? One is the queue. Now the question is, you should be keeping the queue of what? Of integers or of what? See, in this case, each node is represented by an integer itself. So we can actually keep the queue of integer itself, right? Because this is what is representing the node. So I'm going to call it queue itself. And initially, what am I going to push in the queue? I'm going to push the source because that is from where I'm going to start, right? And what is the second thing that I need? I need the visited array. So I am going to again take a vector and I just need to mark it as visited or not. So again, I'm going to take a bool. And what will be the size of this? It is again number of vertices, which is n. And initializing the entire thing is false. Because we are starting with source, I need to first mark source as visited, right? So I am marking source as visited. Now in the example, it is given that the source is 0, but in reality, source could be anything. It is just given to us, right? It could be 1, 2, 3, 4, anything. You need to make sure that whatever the source is, you are marking that as visited. Now you are done with the initial things. Now we need to start the BFS. So till when are we going to continue pushing into the queue and popping into the queue? Till the queue is empty. Remember the second example? So what should be our while loop like? While the queue is not empty, we are going to keep trying again and again. So till it is not empty, I am going to keep trying again and again. So the first thing that I take is I take out the first node that was pushed, right? So that is the first element. I am suppose going to call it current and I am going to take it out like this. So q dot front. And now that I am done taking out the first element, now that I have it, I also need to remove it from the queue. Okay. For C++, you need to take care of it that q dot front doesn't remove the element for you. You need to remove it separately. So here you have just taken out the front and you have stored it in current, but you also need to pop it. Now that you have popped it, you also need to check that this element that is there, is it equal to destination or not? If it is destination, that means you found the answer and you can just return true from there, correct? So if current is equal to the destination, you can just return true from here itself. Otherwise, what do we need to do? We need to go through all the neighbors of this current. How do we go through the neighbors of current? We have to go through the row of the adjacency matrix. What is the length of the row? It is 0 to n, right? So 0 to n minus 1, 0 less than n and I plus plus, right? So how are we going to check that it is neighbor or not? So we are going to see if graph of current and I, if it is true, that means that there is an edge, right? So if the graph of current and I is true, that means there is an edge between it. That means I is the neighbor of current. But I am going to put it into the queue only when, so there is one more condition that I need to check, right? What is the condition? The condition is that it should not have already been visited. The I, which is the neighbor, it should not have already been visited. So if both of these conditions are true, that means that I is the neighbor that has not been visited. So what am I going to do? I am going to push I into the queue and I am going to mark it as visited. Don't forget marking it as visited, and note that we are going to mark it as visited when we are pushing it into the queue so that we don't end up pushing the same elements into the queue again and again. That's it. We are done. If we would have found the answer, we would have returned true at some point. If we have not found the answer, in the end, we are just going to return false. That means the queue must have been empty at some point and we would have come out of this while loop. So now let's run and see whether this works or not. So the cases have run and now let's submit it and see. So just like the last video, here also we have got memory limit exceeded. Why? Because we did BFS, DFS on adjacency matrix, and in sparse graphs there were a lot of false. In this example, you must have seen, right, that there were so many false and there were hardly any trues, right, in the adjacency matrix, because we are just wasting memory and we are going through all of the rows again and again and seeing is it neighbor or not, is it neighbor or not. Adjacency list would be a far more efficient approach over here. So that is why in the next video we will be doing DFS and BFS using adjacency list. So I hope you show up. Before you go, let's quickly discuss the time and the space complexity as well. Let's look at the space complexity first. So we took order of v square to form the graph. Another order of v for the queue. Why order of v? In the worst case, we would have put all of the nodes in the queue, right? So order of v for that, and then visited arrays of the size v. So again order of v. So order of v square plus order of v plus order of v is the space complexity. So order of v square plus order of v plus order of v, you can call it order of v square also. And now let's look at the time complexity. Here first we fill the graph. So here we took order of e to fill the graph. Then what is the time complexity required for BFS? So in the worst case, we will be going through all the elements at the adjacency matrix exactly once, right? We will not be visiting them again and again. So that is why the time complexity of BFS and DFS on adjacency matrix is order of v square itself. So if someone asks you, it is order of v square for both BFS and DFS on adjacency matrix. And now let's look at the code in Java. Coming to the Java code, again we are given n edges. So first thing that we need to do is form a graph which is going to be represented by an adjacency matrix. What is going to be the size of our adjacency matrix? N by n. And I'm going to take a boolean itself because the graph is not weighted. So boolean, and I'm going to call it graph itself, and I'm going to call a new one, new int. And what is the size of it? N by n, correct? Now I first need to initialize all the values to false, right? Because initially nothing is connected to each other. So what am I going to do? For every boolean row that is there in this graph, I'm going to fill the entire thing. So arrays.fill. So I'm going to fill the entire row with false. So nothing is connected initially. And then I'm going to go through all the edges. Again, these edges is 2D array. So it is a 2D array. I have to go through each edge, which is again a 1D array. So there is u and b. So how am I going to go through it? So I'm going to go through it like this. Int edge in edges. And I'm going to have two values inside it. So there is edge of 0 and there is v, which is edge of 1. You do not need this. I'm just writing it like this for simplicity and clarity. Because this is a bidirectional graph, I need to mark both graph of UV as true and graph of VU also. Please do not forget this step and think about these things in an interview. Is it bidirectional or not? So now we are done forming the adjacency matrix. Now we need to start BFS. For BFS, we need two things. What is the first thing that we need? It is a Q, right? So I'm going to make a Q. What values am I supposed to put inside the Q? So if you think about it, our nodes are represented by integer values itself, right? Over here, there is like n equal to 0, 1, 2, 3 like that. So here also in the Q, we can just put that integer itself. So Q of integers, I'm going to call it Q itself. And I'm going to add the source to it, right? What is the second thing that I need other than the Q? I need the visited array. Why do I need it? Because I'm dealing with graphs. So again, it can be of Boolean itself. So Boolean vis, and it is going to be of Boolean. Oh, here I have made of integer. Sorry about that. It will be of Boolean and the size will be of n. And I am supposed to mark the entire thing as false initially. So I can just go like for int I equal to 0, I is less than n, I plus plus, or I could fill also. I'm just telling you that this is one way of writing it. You could also do a fill, okay? So visited of I is false. So now we have a Q and we have the visited array. So now to do the BFS, we need to go over the Q. Till when will we keep going over the Q? Till the Q is not empty, right? Because remember the second example, we kept going over it till the Q was not empty. So while the Q is not empty, I will go through it, and in this, if I find the answer, I'm going to return true. Otherwise, if the Q is empty in the end, I can just return false, correct? Now inside this while loop, the first thing that I need to do is take out the first element in the Q. So how do I do that? I'm going to call it current. I can just do q.remove. So it is removing the first element, right? Remember first in, first out in Q. So I removed the first element. It is there in my current now. Now what do I need to do? I first need to check is it equal to the destination itself or not. If it is equal to the destination, then we have actually found our answer and we can just return true from here itself. Otherwise, we need to go through all the neighbors of current. How do I go through all the neighbors of current? I will go through the entire row. How will I go through the row? I equal to 0, I is less than n, I plus plus. When will I know that this current and I are connected? If basically graph of current and I is true, that means they have an edge connecting them. But in order to put to the Q, first I need to check that I is not visited. If it is visited, I am not going to put into the Q. Remember that, right? So I need to make sure. So if this graph is equal to true and I have not visited this I, only then what am I going to do? I'm going to do two things. What is the first thing that I'm going to do? I'm going to add this I to the Q and I'm going to mark it as visited. And that's it. That is all. This is just the BFS code. So all we did, took the first element, checked if that was our answer. If that was the answer, I just returned true. Otherwise, I went through all the neighbors. I saw that is I the neighbor, and if it is the neighbor, it has not been visited already. If it has not been visited, I can add it to the queue. I can mark it as visited. Make sure you mark it as visited while adding to the queue so that you don't end up putting the same elements into the queue again and again. Let's run it and see. It ran. Now let's try to submit it. Just like last time, here also we got memory limit exceeded. Why? Because we are using adjacency matrix. Now in adjacency matrix, there is going to be a lot of false. So adjacency list is going to give us a better answer over here. Right here, we are going through all the rows simply, right? So we are going to see more optimized code. Basically, using adjacency list, we are going to do BFS, DFS in the coming videos. So make sure you don't miss them. But before you leave, let's quickly look at the time and the space complexity. So here, what is the space that we took? So order of V square for the graph. Again, order of V for the queue. Why order of V? Because in the worst case, all the nodes are going to be there in the queue. So order of V. And we are going to put each node only one time. So order of V max. Okay, worst case. So that is order of V. And for visited also order of V. So order of V square plus order of V plus order of V. You can say order of V square, right? And time complexity is what? Here we have filled the entire thing. Here first we fill the entire thing with false, order of v square, and then order of e to make the edges as true. And then we took the visited. Here, what is the time complexity to do the BFS thing? The time complexity for this is order of v square, because if you think about it, you'll be going through each element in the adjacency matrix at max once, right? And what is the size of the adjacency matrix? It is order of v square. So for both BFS and DFS, for adjacency matrix, our time complexity is order of v square. So I hope you have understood it completely, and I hope you're enjoying this series. I am putting a lot of effort into this. I am writing the code in both C++ and Java, and I wish that you stay with me till at least the end of the series. So please do subscribe. So many of you have not subscribed. Please do hit the notification bell icon. Check out EduCourses if you want to connect with me and you want to have live doubt solving sessions, or if you want to participate in the live courses with me. And keep practicing, keep learning. See you next time.